Right, so let's complete our calculation for the magnetic field from the vector potential. You'll remember we had the following expression for the vector potential in the vicinity of our point of observation. And we're going to take the curl of this to generate the magnetic field. Okay, so here is our expression for A. Here is the way we'll calculate B, and in cylindrical coordinates we have the following expression, rather nasty expression for curl. But the nice thing is that just about every term except 2 in this equation is 0. You'll notice that A only has a phi term. A phi is the only non-zero term. So that means AZ and A rho are 0. So this term is 0. There's another AZ, that is 0. This is 0. And this is 0. Leaving only the terms in A phi. So let's write out our expression now for the curl in the following way. Okay, so if we were now to take this expression and calculate these terms by substituting A phi in here and calculating the derivatives appropriately, we would wind up with the following expression for the magnetic field, and you should check this. Okay, so that's rather an interesting expression. We get two terms. Now you'll notice that this is our old expression for the magnetic field actually on the z-axis at our point of observation. All right, so there it is. We did indeed generate the same result as last time, as we must, but we've generated an extra term as well. There's a rho hat term. You'll notice, however, that this rho hat term is only non-zero when rho is non-zero. In other words, on the z-axis, this term here is indeed 0. Let's think about what this means. It means that as we move off the z-axis, we generate a rho hat bit to our magnetic field. So let's just make sure that that makes sense. If we think about what the magnetic field looks like, here's our current carrying loop, and we're going to have, from the right-hand rule, we know that, and from symmetry, we know the magnetic field lines are going to look something like this, and the direction is like this. So this is our current carrying loop, and these are our magnetic field lines here. Now, on the z-axis, the magnetic field is in the positive z direction. That's what we found. But as we move off the z-axis, you can see we generate a part of the field, a component of the field, in the rho hat direction. The projection of this vector on the rho hat vector is non-zero. So here's our rho hat piece coming in, but it's only as we move off the axis. Now you'll also notice that when we're above the loop in the positive z direction, this part is in the positive rho hat direction. So when z is positive, the projection on rho hat is positive. When z is negative, on the other hand, the projection of rho hat is inwards. This is in the negative rho hat direction. And if you look back at the expression on the previous page for the rho hat component, it depends on z. All right, so positive z is in the positive rho hat direction, negative z in the negative rho hat direction. So this all seems to make perfect sense.